Okay, so let's begin chapter 4. Chapter 4, we're going to look at balancing chemical reactions and kind of using those balanced chemical reactions to look at kind of producing products and how much of the product we're actually producing. The part where we get to stoichiometry, we're going to talk about stoichiometry all along the way, and we'll get there eventually about how we actually do these calculations is kind of the most important thing to pull out of this. Things that are a little bit different here is we are actually probably going to divide this in half. So your next exam is going to cover chapter 3 and 4.1, 4.2, I believe, on chemical reactions and stoichiometry. And then we're going to set the other thing aside. I'm not exactly sure how I'm going to do it right now, but we'll talk about that in class. So writing and balancing chemical equations. So chemical equations. Here we have the representation of a chemical reaction. A couple of things on the left-hand side, we have the reactant side. We'll just highlight it. We have the reactant side. These are all of the things that are occurring. So we're combining together CH4 with 2 oxygen molecules. And then we have this little arrow. There's 2 types of arrows that we're going to run into, but we're just going to talk about the one-sided arrow right now. This is going to be our reaction arrow. You might see things like reacts to give, or oxidizes, any kind of action word, that is going to be your reaction arrow. So when you're doing a word problem, anytime you see that kind of action, something that sounds like a reaction, combusts or reacts to give, oxidizes, reduces, some version of an action word, that is going to be your reaction arrow. You're also going to see some types of modifications. You'll see one in particular. If you see something like that delta above the reaction arrow, that indicates special conditions. So you might see something like this. Let me just zoom in on this. So that would indicate an increase in heat, or it is heated. And you might also see something like, 5 atmospheres. Again, that gives you conditions that the reaction is run under. You're never really going to run into them here, but I just kind of want to make them. So so pressure that we're applying. So those types of things you will see above a reaction arrow to indicate that more is going on, or these are the conditions. You might also see a catalyst there. So if you see something above there, it's probably a catalyst as well. All right. But in this case, we actually don't need either of these to trigger this reaction. On the other side of the coin, we have the product side. The product side are what is produced. So reacts to give, we start with the reactants, they react together, and they give us the products. A couple of things, we can always change the coefficients. So the coefficient out front, we are absolutely allowed to change those. You could double all of those if you wanted to. So we could change this so we had 2, 4, 2, 4, and that's totally fine. What you can't do is you can't alter the chemicals, okay? And we're going to talk about why that's important in terms of balancing. You can always change these coefficients out front. You can never touch the chemicals in place. I can't add, I can't say C2H8 here. I can't double that because it actually makes it a completely new chemical. So never touch the chemicals, only those coefficients that are out front. We're going to start using more regularly. We're going to start using these phase tags. A phase tag is exactly as it sounds. It tells you what phase the substance is in. So here I've got CH4 in the gaseous state reacting with oxygen in the gaseous state, producing CO2 in the gaseous state and water in the gaseous state. So nothing special about that, nothing intriguing about that other than the fact that it's just letting us know what it's producing. So we have 4 phase tags, gas, liquid, and solid. So you should know, does the reactant or the product come out as a gas, liquid, or solid? And then the last one, aqueous, which just simply means that whatever the substance is dissolved in water. And we run into this quite a bit. So we need a special tag for it because we're running a lot of reactions in solution or in water. Okay, so our aqueous phase tag, dissolved in water. Aqueous, say it, aqueous. And there you go. So let's talk about balancing chemical equations. So all of these in the end have to be balanced. Okay, this one is in fact balanced, but we always need balance for one purpose, the law of conservation of mass. The atoms that we have on the left have to equal the atoms that we have on the right. We can't all of a sudden just gain mass somewhere. And so atoms are neither created nor destroyed, and we have to follow that, as in the coefficients need to have an equal number of each atom of each type. So it's never change anything, never change any subscripts. You can only change coefficients. And ideally, we want to use the smallest possible coefficient. So those are the two rules in terms of balancing an equation. And I'll do a couple, and I'll show you the different types that we have. But those coefficients are the only thing that you're allowed to change. So never change subscripts. Never change subscripts basically is just saying don't change the chemical, right? I can't change the chemical. Okay, so never change subscripts, just coefficients out front. And then we're going to use the smallest possible coefficients. So you are going to end up in some situations where you have something like 3.5 water molecules. We don't want decimals either. We're going to have to actually convert those to a whole number. So I could multiply the whole thing by 2, and we would end up with 7 water molecules. Okay, so you're not allowed to have the smallest coefficient possible is correct. And also we need whole numbers. Okay, yeah, so that's kind of what we're shooting for. But before we begin, let's take a look at these. How many atoms are there in each of the following? So I want you to just do those calculations. And this first one, I'll just do the first one for you. I have 4 hydrogens and I have 2 oxygens. And the reason that we're doing this exercise is because we're going to get to the point where we have coefficients as well as subscripts, and we want to make sure that we're getting it. So take a look at these, determine them. We're going to do these in class. So let's talk about the basics of balancing. There are plenty of ways to do it. Some places, some are easier than others. And so let's look from simple to more difficult. If you have an isolated element, this is kind of how I would like you to kind of take a look at this. So I have an isolated element. I have iron all over here. So I am going to put below, just to make life a little bit easier, I'm going to divide this up. I'm going to have, actually, I'm going to do oxygen and I'm going to have iron. So what I'm going to do is I'm going to plug in numbers in order to start balancing these things. And I'm just going to simply cycle through. So I'm going to balance oxygen first. Then I'm going to balance iron, then I'm going to go back to oxygen. So just going to keep going, cycling through, just kind of in order to keep balancing the things out. So first and foremost, let's calculate how many we have before we put any coefficients in. So in this case, I have 1 iron and I have 2 oxygens. And so again, this is the reactant side. And on the product side, I have 3 oxygens and 2 irons. The reason that so I put the elements that I am going to balance underneath, and I'm just simply going to go back and forth balancing these things out. You're going to get good at this, so you don't really have to do this anymore. And maybe don't at this point either, but it's a good way to make sure that you're keeping track of everything. So I choose iron when there's an individual element, like in this case, iron, it's isolated, it's by itself, means that I can add any coefficient and I'll always be able to balance it. So having an isolated element, we always do that one last. All right, so I have 2 oxygens on the left, and I have 2 oxygens on the left, and I have 3 oxygens on the right. So right now we're a little out of balance. So I'm going to throw a coefficient of 2 in front of, I'm going to throw a coefficient of 2 in front of my iron 3 oxide, okay? There's a reason to do this, just because we end up with, we need an even number, because you'll see in a second. So I have changed, because I've added the 2 in front here, I've changed both the iron and the oxygen because they're in the same formula. So I'm going to wipe both of these out and I'm going to calculate again. I've got 2 iron oxide molecules or compound molecules. So I have a total of 4 irons and I have 6 oxygens. So now we're going to take a look at the oxygen again. I've got 2 oxygens on the left and I have 6 on the right. So I need to put a 3 in front here. That's going to change just the oxygen. So I'm going to cross it out. Notice how I'm scribbling it out completely. I don't want to get caught off guard and use the number that's already there. A lot of people do that where they say, oh, I already have 2, so I only need to add 4 more. and it messes people up. So completely scribble it out so you can't see it. I have 6 oxygens on this side. So let's just check one more time. 6 oxygens on the left, 6 oxygens on the right. Iron, I've got 1 iron on the left and I have 4 irons on the right. So I simply need to throw a 4 in front here, and that changes that to 4. And now let's check one more time. 6 oxygens on both sides, 4 irons on both sides. This thing is balanced as written. Okay, so there we go. So that's how we balance out. If you have an isolated element just by itself, do that one last. All right, let's take a look at this one. Isolated element as a molecule. So now I have O2 as the element. So I want to do that one last. So we're kind of choosing the one that we want to do last based on if I put a coefficient in front of the isolated element, it's going to essentially change just that one. So it makes sense to do it that way. So let's quickly do the calculations here, or plug in the values. I have 1 sulfur on the left, 1 on the right. Well, that's good. I've got 4 oxygens on the left and 3 oxygens on the right. Okay, let's balance this out. So I have equal number of sulfurs. Good, we can move on. So I just did sulfur. Now let's check oxygen. I have 4 oxygens on the left and I have 3 on the right. I need 1 more oxygen on the right. Again, all I'm allowed to change are coefficients. So let's throw a 2 in front of the SO3. So that means this changes both. So I'm going to erase those. So now I have 2 sulfurs and I have 6 oxygens. Okay, well, that's not really helpful. Now I've changed both, but you get there slowly just by kind of changing these things one at a time. So I have the 2 in front of the SO3. All right, next up. I'm just gonna make this a little bit clearer. There we go. All right, so now we need, again, cycling through. I've just added a coefficient. Let's start at the top again. I have 1 sulfur on the left, 2 on the right. 1 sulfur reacting, 2 as a product. So I need to change the sulfur. So let's toss a 2 in front of here. I've changed both the sulfur and the oxygen in this case. I now have 2 sulfurs and now here's where the counting, you have to make sure that in this, I have 4 oxygens and here I have 2 oxygens. And I think we're in good shape. We have 6 oxygens here. And that checks out. This thing is balanced as well as written. Okay. So good. So again, I didn't even need to add anything in front of the O2, but if I needed to, I could automatically do that. So we're in good shape here. Everything is balanced. Okay. So that's balancing in a nutshell. You just kind of want to keep track of what you got. And we're going to do a ton of examples of this in class. So if you have problems, we can certainly take a look. All right. Now let's talk about ions. So far we have talked about just looking at individual elements. We can make it a little bit more complex, but actually simpler for us to balance when we take a look at ions. I know that these things are ions because I recognize NH4. I have a polyatomic here. I have a polyatomic here. I know sodium and carbonate. Again, I know that I have a bunch of polyatomics, so I know that these are ions. And again, you get used to this stuff as you do it. So let's balance it, but instead of balancing it, whenever you have ions, this is exclusively for ions. Whenever you have ions, we actually want to balance it by ions as opposed to actual elements. Okay, so instead of saying, all right, I want to balance my nitrogen, I want to balance my hydrogen, my carbon, my oxygen, and going through the whole list, the easier way to do it is to simply say, all right, I have NH4 plus, I have CO3 2 minus, I have Na plus, and I have Cl minus. There are no tricks in terms of which one you do last. And there's a much easier way that I'm going to kind of do in class with you when we get through and kind of understand this a little bit better. But there are my current ions that I have. So on the left-hand side, I have 2 ammonium ions. And on the right, I have 1 NH4 plus, right here. And there's my CO3. Let's look at the carbonate. I have 1 carbonate on the left, and I have 1 carbonate on the right. My sodium, I have 1 sodium on the left, and I have 2 sodiums on the right. In the chloride, I have 1 chloride on the left and I have 1 chloride on the right. So now we have to balance. And so instead of looking at individual elements, now we're just going to do ions. And I guarantee you this is going to, it's going to be much easier to do it this way. So let's start with the ammonium. Okay, so I have 2 on the left, and I just have the 1 on the right. So what do? We're going to toss a 2 in front of this whole thing, and that should give me, so when I toss that 2 in front, that changes my NH4 and my Cl. So I'm going to change my NH4 and my Cl. I now have 2 NH4 and I have 2 Cl. So now we start at the top. NH4, I have 2 of each. We're good. Next up, carbonate. I have 1 of each. Okay, we can just keep moving through. Sodium. I have 2 sodiums on the right and 1 on the left. So we need to take a look at the sodium. Let's throw a 2 in front of there. That's going to change both my sodiums and my chlorides. Now I have 2 of each. And now let's start over. Ammonium is balanced. Carbonate is balanced. Sodium is balanced. And chloride is balanced. We are good to go. We have what we're looking for. It is balanced now. Again, the whole point being we want to just go through and look at the ions as opposed to saying, all right, I've got two nitrogen on the left, I have 1 nitrogen on the right. It's just easier because we know those ions are sticking together. If they're sticking together, it makes life significantly easier. All right, so combustion reactions. So these are a little bit more annoying. We're going to do this in class because there's a reason that I want to talk about it, but there's 2 types of combustion reactions, a complete and an incomplete combustion reaction. Combustion reactions are when you combine a hydrocarbon, carbon and hydrogen, with oxygen, and you get CO2 and water as a product. This is what we get when we burn gasoline, when we burn fossil fuels, you get CO2 and water. This is where all the CO2 comes from in the world, okay? So any combustion reaction is always going to be something burning in O2, but I'm not too worried about all of that right now. What I want to do is I want to balance this out. So we are going to balance this carbon, hydrogen, and oxygen. Why am I choosing oxygen last? I'm choosing oxygen last because it's all isolated. So let's give this a try. I encourage you to pause and try this on your own, but here we go. So I have 3 carbons on the left, 1 on the right. I have 8 hydrogens on the left. I have 2 on the right. I have 2 oxygens on the left, and I have 3 oxygen, 2, 3 oxygen on the right. So now we start to balance. Carbons, 3 on the left, 1 on the right. I'm going to put a 3 in front of the carbon. That changes my carbon, that changes my oxygen. And let's recalculate. 3 carbons, and was that 6? And I have 7 oxygens. Good, carbons are balanced. Let's go to the hydrogens. I have 8 hydrogens on the left, and I have 2 on the right. So let's put a 4 in front. 4 times 2 would give me 8. So that's going to change my hydrogen, and that also changes my oxygen again. Again, I'm just keeping tabs. I'm erasing the number and rewriting. So now I have 8 hydrogens, and I have 6 oxygens here, and I have 4 oxygens here for a grand total of, I'll just underline those, that's not 40 and 60, that's 6 oxygens and 4 oxygens for a total of 10 oxygens. And let's start from the top. Still 3 carbons, still 8 hydrogens. And now the last thing, 2 oxygens on the left, 10 on the right. So very simply, I'm going to put a 5 in front. That is going to take care of, that's only going to change my oxygens. 5 times 2 gives me 10 oxygens. This checks out. Everything is balanced. Good. So that's that. Do the incomplete combustion one. So give this a try. We're going to go over this in class. Yeah, we're going to take a look at this in class. All right. And I think that's pretty much it for balancing. We're going to do these examples in class. By the way, I changed examples so they're like 4.1, 4.2, just so we know what chapter they're from. So yeah, balance all of these, and we'll get into classifying chemical reactions next time.